Section 4.3, Newton's second law of motion. So we're about to get to Newton's second law. That's what comes after the first law. Before we do, first a note. Mathematically, if we want to write the net force, we write this funny looking E with F behind it. So the funny looking E is the Greek letter sigma that denotes vector sum. So this is summation notation, which you may have seen in math class before. If not, that's okay. But it means that you are going to sum up all of the forces. That's all that that's trying to say. All right, now that we have that out of the way, let's take a look at Newton's second law. Newton's second law says when a net external force acts on object of mass m, the acceleration that results is directly proportional to the net force and has a magnitude that is inversely proportional to the mass. The direction of the acceleration is the same as the direction of the net force. So that's a lot of words. For me, I like to think about it mathematically with an equation, and that says that the acceleration that results from a net force is directly proportional to the net force that acts on it and inversely proportional to the mass. So acceleration, vector acceleration, is equal to the vector sum of forces, the net force, divided by the mass. This is commonly rearranged to solve for the net force, and it says that the net force is equal to the mass times the acceleration. So thus, you can walk up to someone and say, may the mass times acceleration be with you, right? And if they're into physics at all, they'll get that you're making a physics joke, which is fantastic. So please go try it. Also, if you do this thing, you might really annoy people. So, you know, just some fun notes. But this is known as F equals ma. That's often the abbreviation. This equation pops up so much. It's going to be the basis for most of our problem solving. So hang on tight to that one because it will be very useful to you. All right, now with that in mind, we can take a look back at our units of force, right? If we know that force is equal to mass times acceleration, then the unit for force, the Newton that we previously said, is going to have the units for mass, kilogram, times that of acceleration, meters per second squared. Or in other words, kilograms times meters per second squared. And so this combination of units is by definition equal to 1 Newton, because that's a lot more compact than writing out kilograms, meters per second squared every single time. But if you ever are uncertain of how a Newton breaks down, you can go back to this F equals ma, and you'll be able to figure it out just fine. All right, so thinking about units, this is following the SI units, where mass is in kilograms, acceleration is in meters per second squared, and the force is in newtons. The CGS system works in dynes, or the British empirical, I think, is in pounds, feet per second squared. So that's just some contrast, but we will be sticking with SI here, so no need to worry about that. All right, so one tip of something that really will help when solving problems is something known as a free body diagram. It's a diagram that represents the object as well as the forces that act on it. So here we have a car. We have two people trying to push the car, and there's an opposing force where the car is not resisting the push and trying to move. Rather than drawing this whole picture out, or really after drawing this whole picture out, because I encourage you to still draw the picture, because this helps give a nice visual and label all of these forces, then we move to something known as a free body diagram, which I'll sometimes abbreviate as FBD. For the free body diagram, we simplify our car down to a single point, since the car is the object of interest. And then we draw all the forces that are acting on the car as vectors, as arrows, with the tails connected to the dot. So even though these two people are pushing on the car, we draw the vectors to the right as though it looks like almost they're pulling on the car, because that allows us to see all of the forces, which ways that they're trying to go. If you draw the arrows as pointing towards the car, then it starts getting a little confusing when we try and combine them. We'll also want to add in our X and Y axis, because we're going to be frequently drawing the force is in reference to the x and the y direction. So that's a really useful thing. And once we've added all these labels in, then we can pay attention to, hey, what would the net force be here with 275 newtons and 395 newtons pointing in the positive x direction and 560 newtons in the negative x direction? Well, that's something we can calculate, right? So if we want to calculate it, we can just take this 275 newtons plus 395 newtons. Those are both positive because they're in the positive x direction. The negative behind the 560s because it's in the negative x direction, right? So we subtract that, and the sum, the resultant of this, is 110 newtons, and notice it's positive 110 newtons because there's more forces pulling in the positive x direction. So once again, plus or minus just tells us about the direction. So this is directed along the positive x-axis of the coordinate system. Cool, so we found out that the net force is to the right in the positive x direction. What does that mean in terms of acceleration? Well, once we can find this net force, right, where we know that this is equal to the sum of all the forces, then we know that we can relate that to the acceleration if we just know the amount of mass that the car or the object has. So if the mass of the car is 1850 kilograms, then by Newton's second law, the acceleration can be calculated with the net force divided by the mass. Positive 110 newtons divided by 1850 kilograms, and that comes out with this acceleration, positive 0.059 meters per second squared. The positive sign here is notable. It tells us that the acceleration is in the positive x direction. So once again, sign does matter, right? So that introduces Newton's second law of motion, which we will get to see how we can connect it to some specific problems in more than one dimension in the next section.